Okay, guys, what I want to talk about today is projectiles that are launched upward at some kind of an angle. Last week, we talked about projectiles that were launched kind of horizontally, and we know that they'll kind of follow a path that goes down and in the shape of a parabola. But what I want to talk about today is what happens if they're launched at an angle instead of just going straight. So we're going to talk about that a little bit, but before we do, I want to review a little bit about what we know with horizontally launched projectiles, like the balls that I dropped off the bleachers last week. So we're going to go ahead and look at a diagram here and think a little bit about the motion of any projectile. So what I'm going to see, you guys might remember, is as this thing is launched, all of the motion is in the horizontal direction. So I would basically just draw a vector that looks something like that, and that vector is going to represent the horizontal motion of that projectile. Now, just the moment it comes out of the cannon, there is no downward velocity. All the velocity is in the horizontal direction. All right? Now, if I go a little bit into the flight, what I find is that the velocity, the horizontal velocity vector, is still exactly what it was when we started. Well, it should look that way at least. But now, because now I notice that there's a little bit of downward motion here too. It's a small amount, not a whole lot, but there is a little bit of downward motion. As I get to this one here, I'll notice that my horizontal velocity is still right about the same length as the first two, but the vertical velocity is starting to increase. Okay. If I go on, I see an even longer vertical velocity, and yet the horizontal velocity still the same. All right, and I'll go through and we'll just continue to add these velocity vectors. We saw this in the video that the horizontal really didn't change very much, but the vertical is going to start to change quite a bit. And finally, when we get to this point, down here at the bottom, I'll move up just a bit, that vertical velocity, I'll go all the way across this text and even further down here, and yet the horizontal velocity is still the same. And you might remember in the previous video, we proved this. If we just kind of drew lines upward all the way up to the top here, maybe I should dash these. Oh, I should have used a ruler on that one. Anyhow, if you look at the distance here between these, remember that what we saw is the distance in between them really was the same. I didn't see much of a difference between the distance between these versus the distance between those, so on and so on. All right, the distance in between each of these positions was exactly the same. So if you have a certain amount of time that passed, you went through the same distance every portion of time. All right, now what does that mean? If I kind of go back, I'm going to go down here. We're going to talk about a couple of questions. What do we know then about the horizontal motion of a projectile? How does the horizontal motion of the projectile behave? Well, if it's covering the exact same distance for every unit of time, I mean, these could be seconds, they could be tenths of a second or 1/20th of a second like we did in the video. But what you notice is that if the amount of time that passes between each one of these snapshots, let's say, if the amount of time that passes between each one of these is exactly the same, and they move through the same distance, their velocity must be constant. All right. So what do we know about the horizontal motion of a projectile? We know that the horizontal motion of a projectile is constant. That is to say, it does not change. Okay? Now, this is making one big assumption. The assumption, W/O, just means without. Air resistance. All right, if you have no air resistance, it will not change. Okay? Now, what about the vertical motion? Well, if I come back up and we look at these, you remember what we did in the video is we basically just got some lines to track these kind of, hopefully these stay horizontal. If I take this line and I go all the way over here, all right, I'm going to get a line that's right about in that location. If I go to the next spot where we took a picture, where we know what the location is, I'm about in that location. If we continue down, I'll just do all of these. Hopefully they're fairly straight and even lines for all of them. So what we know is that the location vertically of the ball, does it change regularly? Meaning, do I get the same difference between the two lines as we saw up here? Well, what I see is between the first two intervals of time, I have a very small distance right there. Then it gets a little bit bigger here, and a little bit bigger still here, and even bigger here, and then this final interval is the biggest of all. So what I can say is that the distance between the location of that ball vertically changes all the time, even though we're taking these snapshots at the same time interval. So 0.2 seconds, 0.2 seconds, 0.2 seconds, 0.2 seconds, 0.2 seconds. And yet we go through a bigger distance in this 0.2 seconds than we did in this 0.2 seconds. And we went through the smallest distance of all in the first 0.2 seconds. So same amount of time, but vastly different amounts of vertical distance that you covered for each one. Remember that what that must mean that this is not constant velocity like we saw horizontally, but it must be a change. The motion here must be changing if I'm going to cover more space in the same amount of time down here compared to here. So what we would say is this motion is accelerated. All right, this motion must be accelerated. All right, so if we go down here and we answer these questions, again, I'm just reviewing what we went over in that video right now. What about the vertical motion then of a projectile? Is it constant like we set up here? I'll go with red, it'll stand out a little better. The horizontal motion we said was constant. What about the vertical motion? Vertical motion is certainly not constant. We'd have to say that this motion, it is accelerated. All right, it is accelerated. All right, it's changing. Just note that too. Velocity is changing. So what do we call changing velocity? That's called acceleration. So this is accelerated motion. Well, my next question, and we didn't go into it in the video all that much, but I'd ask why. I mean, this object's flying through the air. Why is it that vertically it's accelerating and yet horizontally it's traveling with constant velocity? It would seem to be you're moving through the same stuff. Why is this true? Well, what we can say is that in the vertical direction, right? In the vertical direction, you have a force. At this point, I'm sure some of you guys know the force that I'm talking about. It's gravity. And that's going to cause the speed to change in the direction that the force is acting. Well, what direction does gravity always act in? It always acts vertically. So in the vertical direction, you have a force, gravity, which causes speed change in the vertical direction. So what must that mean then about a horizontal? What must be true about horizontal motion? If I have a force that causes speed change in the vertical direction, we know it's gravity. So I see a speed change vertically, but I don't see a speed change horizontally. What does that mean then about forces acting in the horizontal direction? If I don't see a speed change, so we'll just say horizontal, no speed change. And really, I could say velocity here. No speed or velocity change means no force. All right? And I'll just say no force horizontally. All right, you guys. So basically, when it comes down to it, this is the why. In the vertical direction, there's a force acting. It's gravity. Gravity always goes downward. So this is going to cause a downward speed change in the vertical direction. The fact is, you don't see, the evidence here is I don't see a change in velocity horizontally, no speed change horizontally, which means there must not be a force horizontally. This is one of those things, you guys, in the real world that is a cut and dry. This works every single time. It's one of the reasons why I like things like chemistry and physics, is because you have a set of rules and never, ever, ever do you deviate from them. All right? I'm going to get the same results. If I drop a ball from a certain height, it's going to be moving at a certain speed every single time. I could do it 50 times, and I should get a number that's extremely close to the same number each and every time. All right? If there's a force, you're going to get an acceleration. If there is no force, you won't get an acceleration. It is as simple as that. So we know that about projectiles that are launched horizontally. But today what I want to do is I want to look at a different example. Instead of a horizontal, my paper straight away here, we're going low tech today, except for the fact we're videotaping this. All right, I want to think a little differently now. Instead of thinking about a ball that is dropped horizontally, now I'm going to think about a soccer player where the player is going to come up and kick this ball. All right, it's going to come up and kick this ball at some angle. And so we can see that the initial angle that this ball takes off at is kind of in that direction. Okay? Now, if you think about this, in order to achieve that direction, this is really the kick that he puts on this, the force that he puts on this ball is really made up of two vectors. One is upward. All right? One is going upward. So he kicks that ball and gives an initial upward velocity, but at the same time, he also is kicking it forward. So he's also giving a forward velocity that's going off in this direction. And if I had to guess here, I would say it's pretty close to a 45. So these two forces or these two velocities, I should say, are exactly the same. So that if I were to basically add those up, if I took this red guy right here, and I'm just going to slide him right over here. This is totally legal, by the way. And I'm just going to say, all right, we're going to put him right, slide him all the way to the end of this one. Why would I do that? Because I'm connecting the head of this one vector, the dark blue one, with the tail of the red one. I'm adding those two. And remember, when we talked about vectors, I could basically say that this pair of vectors, this plus this, is exactly the same thing as this, the path that the ball actually takes. Now, let's say that that ball flies up into the air, and no longer is his foot in contact with the ball. As soon as that comes off his foot, he's no longer in contact with this, and this ball's flying through the air. What you could say is he has no control at all over the ball now. Isaac Newton and gravity have all the control. So let's think about what's going to happen to each of these two vectors as that ball goes up into the air. As it goes up into the air, what do we know about the horizontal velocity? The horizontal velocity. Is there any force acting in the horizontal direction if we assume there's no air resistance? Right? In the absence of air resistance, there is nothing to slow down this velocity. And so it just keeps going at that same speed. And so what I would say here is that my vector, I'll try to do this at least to scale, although when we do mathematical questions like this, we don't really have to worry about scale nearly as much. I just want the diagram to look decent. So it looks like to me that that vector is about 15 millimeters, 1.5 centimeters. So I'm going to kind of draw him right here. Okay. I'm going to draw him right here. Now, what do we know about the horizontal velocity of all of these locations? Well, going back to that last page, the one thing that we do know, where did I put it? Here it is. The one thing that I know about horizontal velocities is the horizontal velocity is always constant. It doesn't change. So if I assume we have no air resistance, then I would say that every single one of these locations where the ball is should have the same length of its horizontal motion. So they should all be about this long, and they're all in the same direction. So I'll go over here, draw that one, and finally, look at this last one over here. So they're all my horizontals. Again, none of them changed. Why? There's no force to change them. But what about the, switch over to my red. What about this velocity vector here, the vertical one? Well, it left its foot with an upward vertical velocity, a positive vertical velocity. But what's gravity going to do to that? Well, gravity is going to act on that, whatever that velocity is, and at some later time, gravity will have pulled this down. It will have slowed this ball down so that this upward vector is no longer going to be as long. Is it still going upward? And the answer to that would be yes, because we know this is the peak. And that's the point at which it turns around and starts coming back down. And so I would say that my vector for my vertical velocity at this location should be a little shorter than this one. Okay? Gravity's pulling it down. It's changing that velocity to a less positive one. So I guess we could say, you know, maybe this was 15 meters per second. Well, here, remember, gravity's negative 10 meters per second squared. So here, instead of 15, it's changed, let's say, by negative 10. So now it's positive 5. Actually, that wouldn't work because this one at the peak should be 0. So I don't have any upward velocity here. All of my velocity is in the forward direction, in the horizontal direction. Okay? Now, on the way back down, gravity's continuing to pull on this ball. It's pulling this ball, even right here at the peak, gravity's trying to pull it down. So at this point, it has a velocity, and I'm going to call this Vy. So the velocity in the y direction, the vertical direction, is 0. It has no speed right there. Gravity's taken away all of its velocity. All right. Now what's happening? Well, now gravity's continuing to pull down. And as time continues to go on, it actually starts to make this thing pull downward just a little bit. Okay. It's going to start to pull it downward. It's on its way down vertically. All right. And then when I finally get back to this location, it's going to pull down even more. Pull that down just a wee bit more. Now, if this height is the same as this height, and we know gravity won't change, it's going to slow it down, slow it down, slow it down to 0. And then it's going to speed it up, speed it up, speed it up until the downward speed here, if you're at the same elevation, the downward speed here and the upward speed here should be identical. They're just in opposite directions. That's why I extended this line a little bit. I was trying to match that. Okay. So do you really see any change compared to the horizontal launch? I mean, does the ball behave any differently if it's launched at an angle as compared to when it was launched horizontally? When you think about it, there really is no difference. We could say that horizontal velocity is still constant. Nothing changed there. And vertical velocity still changes. And I would say not only does it change, it changes very predictably. Very predictably with gravity. Okay? You still get the same changes here. Fact is, if I look at this drawing, you guys, and I just lopped off this part right here, I would basically, this final part of the drawing would work just like it did when we threw those balls off the bleachers. All right? This is the shape that it took. Okay, it took the shape of a parabola. All right. So one other thing that you can do, and I did it here, is that if I combine these two vectors, the vertical and the horizontal, if I combine those two by connecting head to tail, I get the path that this thing takes. If I were to slide this guy over here, he's going to take that path right there. Notice it's the path that the ball is flying with. There is no vertical one here, and so the only one here is this ball is flying completely horizontally. Okay, completely horizontally at that location because there is no vertical. Here, if I slide this guy over to here and draw him, just take him and slide him over there and then draw him, there's the path that he would be taking at that moment in time. And if I look at this one, slide him way over here, there's the bottom, here's the path. The resultant of these two vectors basically shows where that ball is moving at the very end. And so you could predict this motion by simply adding the two components, the horizontal and the vertical. If I add those two together, I get the velocity at any moment in time. Now, I'm going to ask you a question here. And I want you to think about this for a second. I'm going to pause and let you guys think just a bit. Where in the flight of this ball is the ball moving the slowest? The slowest. Where in the flight of this ball would the ball be moving the slowest? Take a second and think about it. See if you can figure that out. You got 5 possible answers, right? Okay, here we go. Think of it this way. I've got a line this long on every one of these, right? The blue line. And then if I add the vertical vectors here, at least on these ones, I'm going to end up with the actual total velocity being the resultant that's right here. Now, Notice this is the hypotenuse of a right triangle. And the hypotenuse of a right triangle is always bigger than either of the two sides. So if you think about this velocity when you first kick the ball, it's going to be greater than the forward velocity. This velocity when this ball's in this position is going to be greater than this forward velocity. But what happens here? Here, there is no triangle. This is the only velocity you have. And so if you think about what's happening as you go from here to here to here, that hypotenuse is it's bigger here, it's a little smaller here, and here, the hypotenuse is this line. So the slowest position that you're ever going to see in any projectile, the slowest velocity, is going to be right there at the top. The reason? All of the velocities made up this horizontal component, and there is no vertical component that would get added to it. So there is no hypotenuse that would be longer than this horizontal component. All right? So your slowest position is always going to be the peak. If you're at a baseball game and a foul ball gets hit and you want to catch it with your bare hands, oops, the fan blew it right off. You want to catch that ball with your bare hands. The best place to catch it is right at the peak of its flight. That's where it's moving slower than anywhere else in this flight. Okay? So catch that sucker right at the peak. You're going to have to sit in the second deck or something. All right, you guys. So that's a little bit about projectiles here. Now I have another diagram that we're going to look at that talks about how angles cause changes in the flight of a projectile. So you notice I'm looking at this diagram that has a bunch of soccer balls being kicked at different angles. Now I want to introduce one thing to you guys, and that is a term called range. What is range? Range is the horizontal distance a projectile will fly after launch. Now, would you say that, look at the diagram, would you say that that range is determined or has something to do with the angle at which it was launched? Just a bit. Looking at the diagrams here, would you say that the distance that these projectiles will fly, 15 is going to go to here, 75 is going to go to the same spot? That's more than a coincidence. 30 goes to here, but so does 60, okay? And 45, it actually goes off the diagram a little bit. Do you think that angle has something to do with range? It definitely does. So I'll go down to the bottom here since we're talking about it. What angle gives the maximum range? Well, if I look at this, I can see that of all of these, 45 seems to give the longest range. If I go higher than 45, so if I go up to 60, it's shorter. If I go lower than 45, I go down to 30, it's also shorter than 45. So our maximum range is going to be 45 degrees. Okay? Now, why would it change with different launch angles? Okay? Why would it change with different launch angles? Well, think of it this way. If you come in and you kick a ball at 75 degrees, that's your angle of launch. But remember that this angle is really made up of two components. It's made up of a horizontal component, right? It's going to be made up of a horizontal component, but it's also, if I add in, it's also made up of a vertical component. And what about those two? What about the horizontal component versus the vertical? Well, I can see the horizontal is very short. It's not very long. That means it's not traveling very quickly horizontally. But it's really tall. The vertical one is really tall. That means It's traveling really fast going upward when they first kick it, but not very fast going forward. Now, what's going to control the amount of time that it's in the air? It's all about the vertical. The more velocity I give it vertically, the higher it's going to go, and it'll be in the air for a really long time. But your problem is, you get a big horizontal or big vertical component, it's gonna be in the air a long time. So in fact is, we'll label that. I'll just say in air, long time. All right, that tall vertical component there means you're going to be in the air a really long time, but you're not moving forward very quickly. So I'll say moves, hopefully you guys can read, yeah. Moves forward slowly. Okay, so this line here is going to control the forward velocity. This one tells you how fast you're going upward, which controls how long you're in the air. So think of 75 degrees. 75 degrees is going to be in the air a really long time because you kicked it mostly upward. But it's not going to be moving forward very quickly. All right? How about 60? Well, I can see if I look at 60, and I can tell right now, I'm going to make a huge mess out of this. But if I look at 60, its launch angle is going to be like this. Okay? Which means you're going to have a little bit more forward speed, right? A little bit more forward speed, but not quite as much upward speed. So that means it won't be in the air quite as long, all right? But it does have more forward speed. So when it is in the air, it's traveling forward more quickly. Well, that helps explain why it had a longer range, okay? It had a longer range because although it wasn't in the air that long, it was moving forward more quickly, okay? If I go to the 45, once again, let's mess this up even more. That's kind of the angle that my 45 goes at. And what you see here is it's pretty much a trade-off, okay? It is gonna have its forward velocity is right here. Oop, check that. That's its vertical, but its forward, notice, its forward velocity, this line down here is longer than the other two, meaning it's moving forward quickly, more quickly than the others. But its vertical velocity is not as high as the other two. So it's in the air less time than here or here, but it's moving forward more quickly. All right, so it's what 45 does is it kind of trades off. You get much faster forward motion, but you're not in the air quite as long. The trade-off, though, gives you the longest range, is the way it works. So I would tell you guys, if you've ever played in a basketball game, you've done this before. If you ever watch someone who's really good running for a layup, what you'll notice is when they get close to their basket, that last step that they take, they're running as fast as they can down the court, but that last step that they take, they allow their knees to bend a lot. They allow their knees to bend much more than when they're running, and then they spring straight upward. What they're trying to do there is they're trading off forward speed for upward speed. Because if you're not good at shooting layups, usually what happens is you're running too fast. If you're moving too fast, when you go to lay that ball up against the board, the ball's moving at the same speed you are. If you go to lay that ball off the board, it hits the board too hard because it's traveling more in the horizontal. It hits that board too hard and bounces over the top of the rim. You didn't slow down enough. So you have to trade that forward running speed for upward jumping speed. And again, the trade-off means I'm going to rise upward more than I go forward. And when I lay the ball off of the backboard, it doesn't bounce so hard because it doesn't have that forward velocity that would make it bounce. And it just drops into the rim, hopefully. All right. On the other hand, if you look like a long jumper, if you got a long jumper in track, they want a lot of that forward speed. So they don't convert quite as much into upward speed, but they need enough to keep them in the air for a certain period of time. All this comes with training. But it's always a trade-off between these two vectors, the vertical velocity and the horizontal one. Okay. I had one other thing I wanted to talk to you guys about, and that is the idea of real projectiles that really do have air resistance. Okay, so what I'm going to do here is I'm going to switch over. I'm going to share my screen with you guys, and I'm going to switch over to a computer app. This is a family of simulations called PhET simulations, and they're made by University of Colorado, and we're going to kind of just look at one of these for a few minutes here. So what you guys are seeing here, it basically is used to measure projectiles, and I have the ability to either, you can see over here, to either turn on air resistance or not turn on air resistance. So what I'm going to do is I'm going to say, what's going to happen if I have no air resistance? Let's lower this to say 75 degrees. I have no air resistance and I launch at 10 meters per second. So we want to kind of look at some of these relationships. Well, let's see what happens without air resistance. I'm going to go ahead and fire a projectile here. You see, it really doesn't go very far. Okay. Let's keep that same speed, 10 meters per second, no air resistance. And again, I'm going to fire at 10 meters per second, and I can see it goes a little bit further. Now, what are you predicting here? Based upon the diagram that we just saw, we just looked at, what's going to happen at 45? What we should see at 45 is it goes the furthest. Here it goes. All right, you see it goes a little bit further than 60 did, and further still than 75 did. And if I drop this down to 30, which I think is what they did in that diagram, we'll do it one more time. And you'll see it goes the same distance at 30 as it did at 60. So this is just kind of showing you in a simulation what we saw before. Now I'm going to go ahead and clear those. Let's go back up to 70. Check me, 75. And I'm going to keep it at 10 meters per second. And we're going to launch. Okay, we get this range. Now what I'm going to do though is, this is physics world. If we're flying, we don't have no air. All right, we have air. We have air resistance whether we like it or not. So now if I fire this, you'll see what's the effect of air resistance. What about the height that it goes to? Doesn't seem to go to the same height, seems to be lower, and it doesn't go as far. Resistance never pushes you along, it always slows you down. Okay, if I do this at 60, we'll see the same thing. Again, no air resistance, there it is. Air resistance, here it is. Oh, we hit the guy. All right, so notice, not as high, also not as far. Air resistance always slows you down, never speeds you up. Let's crank this up. Let's say we're at 20 now. All right, I'm going to turn air resistance off, but you'll see the exact same effect. Nothing really changes here. Just did get on the screen. What's your prediction? When I do turn on air resistance, what's going to happen now? Let's see. Again, with air resistance, you don't go as far. Your range is shorter and your height is shorter. This is true for every single projectile. What do you notice about the shape? Look at this kind of pinkish purple shape you see here versus the blue. The blue one, perfect parabola. I mean, it's symmetrical. There's the high point right there. It is perfectly symmetrical on this side versus that side. What do you notice here though? There's my center point right there. And I see it looks more like a parabola here. But on the downside, it kind of flattens out. It doesn't go nearly as far as I expected it to. This end part here just kind of dies. Well, why would it do that? What really is changing? What's really changing here is your horizontal velocity is no longer constant. All right? What's air resistance going to do? If I'm flying horizontally like this, air resistance is going to resist my forward velocity and slow it down. So the longer that air has to work on this, the shorter this section is, meaning you don't have that horizontal velocity that you did before. They're getting closer and closer to each other, and so it almost goes flat. Okay? So in the real world, what we see, all right, in the real world, what we see is that your projectile will go neither as high, it won't go as high as it would if you have air resistance. It also how would I say it? Doesn't have the same shape. It's shorter. It doesn't go, its range is shorter, and that end part is flatter, I guess I could say. So not as high, not as far, and the shape is flat. Okay, this is the way the projectiles really look in real life. So I would say, well, why do we bother then? Why do we have no air resistance when we solve these questions? Why do I choose to say, well, with no air resistance? Well, this is all about simplicity, you guys. The problem with air resistance is it changes. Air resistance changes with your speed. So as air resistance slows you down, what actually happens is the air resistance that you have is going to change. And so that's a calculus problem, and we're not in for calculus. Okay, so that's why we assume we don't have air resistance. This projectile stuff would work perfect if we were on the moon. It doesn't quite work perfect here on Earth. I will tell you it works better when the object is small, because the small objects have less air resistance. So that's one of the big things. And also when it's not moving fast. So for instance, if we were to toss a ball to somebody, it's going to look much more like we've talked about with no air resistance. If we're shooting a bullet through the air, or we're hitting a golf ball at really high speed, what you'll actually find is the air resistance is going to make a bigger difference. Okay. All right. I'm going to wrap this up, you guys. This is kind of mostly the last part of projectiles we're going to do. We're going to talk about how satellites work in the next video. But for now, this is a review of upwardly launched projectiles, and also of the way that drag works, air resistance works on projectiles itself. We'll see you next time. Bye-bye.